In this video, I would like to talk about finding the area under a graph using Riemann sums. And we're going to first talk about approximating the area using rectangles, and then finding the exact area using limits. So let's start with what I mean visually. Let's say I'll just draw a nice simple function, maybe something like this. And let's say this is the interval a to b. And I'm going to draw two copies of this actually. So the same graph, same interval a to b. And now when we're approximating the area under the graph, or the area bounded between the graph and the x-axis, we can approximate this area using rectangles. And to find the height of the rectangle, we have to plug an x value into our function. So this is our function f of x. And we have to plug in a value. So we're going to use multiple rectangles, but I'll just draw one generic rectangle. And one option is to use the left endpoint of each subinterval. And we'll call that left endpoint. So the area of this rectangle is given by base times height. And we'll talk about what the base is in a moment. But the height is what you get when you plug in this x value into the function. And that x value, we're going to use lowercase m sub I. So mi is equal to the ith left endpoint, or the minimum value in the ith subinterval. And so the height of that rectangle is whatever you get when you plug that x value into your function. And another option is to use the right endpoints. So I'll draw the same rectangle, but instead of intersecting the graph on the left side, it'll intersect the graph on the right side. So this rectangle, so it looks like, with the function I've drawn, this isn't always the case, but the way I've drawn this graph, it looks like if I use the left endpoint of each subinterval, it's going to be an underestimate of the actual area. And if I use the right endpoint, it'll be an overestimate. And so the height of this rectangle is whatever I get when I plug in this x value. And I'll call that capital M sub I. And this height, or this y value, is whatever we get when we plug that x value into our function. And so capital M is what we'll use for right endpoints. So M sub I will be the ith right endpoint. So basically what we do is we take that interval a to b and we split it up into subintervals. So let's say we're going to be splitting the entire interval a to b up into n subintervals, meaning, so if there's n subintervals, that means we're using n rectangles. So if we want to use 5 rectangles to estimate the area, then n is equal to 5, and so on. Now, what I want to talk about is how to find a formula for these endpoints. Whether you're using the left or the right, it doesn't matter. And it actually turns out that you don't have to use an endpoint. You could use the midpoint or any other value in each subinterval to plug into the function to find the height of the rectangle. And so these are sometimes referred to as left Riemann sums and right Riemann sums. But a Riemann sum is just using rectangles to estimate the area under a graph, or the area bounded between the graph and the x-axis. So let's look at what we're doing. Let's look at the interval. Let's just go on the number line, the interval a to b. So here's a and here's b. Now, if we're splitting this interval up into n smaller subintervals, or n equal subintervals, let's say delta x is the size of the subinterval. So delta x, which is basically, so delta x is going to be the base of the rectangle. So the length of the base is going to be delta x. And so delta x is going to be, well, it's the length of the interval, which is b minus a, that's the total interval, and divided by how many rectangles we're using. So we're going to say delta x is equal to b minus a divided by n. And so if we're splitting this interval up, well, the length of that interval, that's going to be delta x. So the value of the endpoint, the right endpoint of that first subinterval is going to be a plus delta x. And then the next subinterval, it's another value of delta x. So the end of that second subinterval, it's going to be whatever you're starting with, the a plus 2 delta x's. And so on. And we could repeat this process. There's another delta x. And so this value here will be a plus 3 delta x. And so on. And then when we finally get to that last subinterval, which is again, the length of that last subinterval is delta x. Well, there's n of them, n of those subintervals. So this value of b is going to equal a plus n delta x. And this first one, we could say that's a plus 0 delta x. Which means if the end value of that last subinterval is a plus n delta x, well then the starting point, or the starting value, would be a plus, well, 1 less, n minus 1 times delta x. So what I want to do is come up with a formula for any generic subinterval. So what is the starting value and ending value of the ith subinterval? And so that's what I want to do here. So let's say somewhere over here, there's a subinterval. And so we're going to call this left endpoint. This is the lowercase m sub I, and the right endpoint, this is going to be the uppercase m sub I. And that's what we want to focus on here. Is what is a formula for the left endpoint? What is a formula for the right endpoint? All right, so let's explore this a little bit. And I'm going to make, I think I'll make a little table of values. So the interval, the right endpoint, and the left endpoint. Okay, you'll see what I'm getting at in a moment. So, and this is just looking at this number line I have right above it. So the first interval. In that first interval, the left endpoint is a, and the right endpoint is a plus delta x. And the second subinterval, looking above, so this is the second subinterval. This would be the third subinterval, and so on. This is the first one. First. So the left endpoint of the second subinterval, according to that number line up there, is a plus delta x, and the endpoint is a plus 2 delta x, and the third is, let's start down here, a plus 2 delta x up to a plus 3 delta x. And then we've made it to the last, or the nth subinterval. And that nth subinterval on the left, the starting x value is a plus n minus 1 times delta x, and the ending value of that last subinterval is a plus n delta x. So this is the nth subinterval. Okay, so based on this, so this is the, let's be more specific, let's say this is the ith interval. When I is equal to 1, it's the first interval. When I is equal to 2, it's the second. When I is equal to 3, it's the third. So the right endpoint, which we're using capital M sub I, and the left endpoint, which we're using lowercase m sub I. Well, if you look at this table that I've started up here, for the right endpoint, the number of delta x's is equal to I. So in the first for the first interval, if you're looking at just the right endpoints, for the first interval, when I is equal to 1, there's 1 delta x. When I is equal to 2, there's 2 delta x's. When I is equal to 3, there's 3 delta x's. So it looks like for the right endpoints, it is a plus I times delta x. A plus I delta x. And if we look at the left endpoints, well, when I is equal to 1, there's no delta x's. When I is equal to 2, there's 1 delta x. When I is equal to 3, there's 2 delta x's. So for left endpoints, the number of delta x's looks like it's 1 less than I. So for left endpoints, we could say each left endpoint is equal to a plus, well, I minus 1 times delta x. And so now we could use this because we're going to have to, if we're estimating the area by using a bunch of rectangles, the area of each rectangle is equal to base times height, right? And if the base of each rectangle is delta x, well, the height is coming from, well, you have to plug in an x value into your function to find the height. So if we're using right endpoints, if we're using right endpoints, I'm just going to redraw quickly that graph from up there. If we're using right endpoints, then this rectangle here is going to have a base of delta x and a height of, well, whatever it is when you plug in that right endpoint into the function. So if the right endpoint is mi, capital Mi, then this is f of capital Mi. And now we have a formula for the right endpoints. So the height should be the function value when you plug in a plus I times delta x. And so the area of the ith rectangle should be equal to f of a plus I delta x times, make this a little bit smaller, times delta x. And so if we add up all of those rectangles, so it'll look like something like this. So if we add up all those rectangles, that's our approximation for the area. And by that same logic, if we're using left endpoints, well, we're plugging in lowercase mi, or the x value, which is the left endpoint, and the height will be f of m sub I. And so that rectangle, if we're using left endpoints instead of right, well, the base is still delta x, and the height will be whatever the y value is when you plug that x value, that left endpoint, into the function, which is f of a plus I minus 1 delta x. And so the area of the ith rectangle would be, again, the product of base times height. Now, it turns out that if we're not looking for an approximate area, because if we're just based on these diagrams, if we're using a finite number of rectangles, you're going to get a different answer with using left endpoints versus using right. Because in this particular case, it looks like right endpoints will be too much. It will overestimate the area, and left endpoints will underestimate the area. But if we take that value of n, the number of rectangles we're using, if we let n go to infinity, as n goes to infinity, well, delta x goes to 0. Because if you're using more and more rectangles, then the length of each subinterval is getting smaller and smaller. So as the number of rectangles gets infinitely large, the width of each rectangle gets infinitely small, which means the left endpoint approaches the right endpoint. So when we apply limits, it actually doesn't matter whether we use the left endpoint or the right endpoint or any value in between. So the exact area from on the interval a to b under the graph, or bounded between the graph and the x-axis, is equal to the limit as n goes to infinity of the sum of all those rectangles. And the sum of those rectangles, I goes from 1 to n, of f of lowercase mi times delta x. That's if we're using left endpoints. And that's also equal to the limit as n goes to infinity of the sum of all those rectangles using right endpoints. Now, without the limits there, these two things are not equal. All right, so if we go back to talking about the approximate area, well, just the sum of a finite number of rectangles using the left endpoints is not equal to the sum of those same n rectangles, but using right endpoints. The only time we have equality, so this is if we're just estimating or approximating the area, they're not equal. The only time we have equality is when the number of rectangles we're using goes to 0. So these are referred to as the left Riemann sum and the right Riemann sum. But the Riemann sum in general says, well, you don't have to even use an endpoint. You could use any number. And so more generally put, the exact area between the graph and the x-axis on the interval a to b, well, that should be equal to the limit as the number of rectangles goes to infinity of the sum of the area of all of those rectangles, where the height is given by just plugging in any x value into the function, where c is any number between the left endpoint and the right endpoint, or it could be equal to the left or equal to the right. Since, to find the exact area under the graph, since you could use any value in the interval from the left endpoint up to the right endpoint, you want to pick the most convenient one. And it turns out, and you'll see in my next video when I work through an actual example, that the most convenient choice of CI is the right endpoint. And the reason why, and let me just scroll back up in a minute, or in a moment, but the reason why the right endpoints are more convenient to use when you're actually plugging them in and doing actual calculations. The reason why the right endpoint is more convenient than the left is right here. Well, the left endpoint has an I-1, and the right endpoint has an I. So why pick the I-1 when you could pick the I? If our discussion leads us to, you could pick any number in the interval, the left endpoint, the right endpoint, or any number in between, pick the most convenient one, and that's going to be the right endpoint. And that's what I'll use in my next video, where I give you an actual function and find the exact area under that function, under the graph of that function, using the sum of rectangles and taking the limit as the number of rectangles approaches infinity. This video was just explaining the general topic of setting the problem up, or how to find a formula for the endpoints and which endpoint to use. Okay, so again, my next video, I will be going through a specific example, start to finish. So that's it for now. I hope it was helpful.